Okay, good morning everyone. So last week we have already talked about some basic definition related to reliability, and we have been using as a time-dependent dielectric breakdown as one example to illustrate that reliability is a stochastic process that can be terminated by a threshold. So stochastic means that this kind of process has a random probability distribution that can be analyzed statistically and not be able to predict precisely. So that's why for the future course, we will also talk about some basic statistic tools that allow us to do the reliability analysis. Okay, so we will continue to discuss what is reliability. So another important factor when we consider reliability is specific conditions here. So specific condition, it means that we need to clearly define the testing condition. Specification of the product testing. Or operation conditions. Is essential in predict reliability. So every time when we talk about reliability, we also have to be very clearly to understand what is actually our specific condition. So for example, elevating the temperature is a universal way to accelerate the value. In most of the time, when we try to heat up our semiconductor device or semiconductor electronics at high temperature, is always try to accelerate the degradation. That means we try to accelerate the values. Therefore, it makes big difference whether the test temperature is at, for example, 25 Celsius degree or 155 Celsius degree. So that's actually give us a huge difference. So it need to be very clearly careful about this when we do our reliability testing. It makes a huge difference between the specific condition. In here, of course, not only for the temperature, but also we have to be very clearly define the bias. Also, of course, the temperature. And sometimes beyond the bias temperature, we also have to be very careful about other factors. For example, the humidity. And so on. So these are all the specific conditions that we need to be carefully understand when we start to do the reliability testing, or we start to define the reliability specs here. So similarly, other specifications might be the level of voltage, humidity during the testing or use. So when we talk about reliability, it has to be correlated with what kind of condition for reliability. So that's important. And another factor is we are very often use elevating the temperature, because elevating temperature could give us accelerating the values. But why do we need to accelerate the values? Because we need to test our device in the reasonable timing that can give us the chance to do the estimation. So for example, let's say if we try to stress the device, we try to test the device at 25 Celsius degrees, and then if we give the bias, for example, the gate voltage of 5 volt, and probably the device will be only fail, or the device will be only have the degradation or completely failures after 5 years. But of course, if you try to qualify, do the reliability testing of this device, it's not possible. You will stress this device for 5 years. So usually we will start to do the acceleration testing. So one of the easy way to do the accelerating testing is we start to stress the device at a high temperature. For example, we will put our device in a high temperature environment, for example 150 Celsius degree, and the goal is we hope to accelerate the failures. So still the same, we will stress at the VG 5 volt here, but because this is a high temperature testing, although it's with same bias condition, but our device might start to have the failure earlier. For example, probably we can already see the device have the failures within 1000 seconds here. So now with this 1000 seconds, that is a reasonable time range that we can be conducted in the lab or in the company, because we were not possibly to test the device for 5 years. So usually we have to minimize the testing time here. So 1000 seconds is possible to be conducted in the lab here. So therefore, after we obtain this kind of the information, the final step is we still would like to understand what would be the failure time at the room temperature. So at this moment, we need to apply certain model. So we need to develop the model for the lifetime prediction. At the 25 Celsius degree. So that's one of the main purpose we do the accelerating testing. Sometimes we don't want to see the failure, but in order to predict the lifetime in the range that we are interested in, so we need to do the accelerating testing. So we hope to see the failure can be happen in the timing that reasonable for us. So this is one of the case, and this case is very useful because in all of the reliability testing, we always do the accelerating testing. So again, original, we would like to know what would be the failure time at the room temperature with this bias, but probably this device can survive for more than 5 years. So that's not possible. Allow us to do the testing in the lab, because 5 years is a pretty longer time. So what we often do is we start to do the accelerating testing. We assume that our degradation can be accelerated under the high temperature. So we'll heat up the device at 150 Celsius degree, and with the same bias, the device can start to degrade at 1000 seconds. So now, once we have this information, we still need to convert back to the case at the room temperature. So that's why we need to have some reasonable model, give us a certain lifetime prediction at 25 Celsius degrees. So this kind of procedure is very often used in the reliability testing and also the modeling and also the prediction. Okay, and the next is as long as when we talk about the reliability, the most important part is how do we define the value. The value can be considered in the many different definitions here. So therefore, the question of what is meant by value must be addressed. So first one, does it mean the device is an actual fracture or actual breakdown? Actual fracture or actual breakage. So that means that the device is completely broken. So that for sure, that can be defined as a value here. But sometimes probably we won't prefer this definition because of the usually the certain characteristic shift to a certain amount, that's already enough that for us to define as a value. So the second one, the value does it mean some degree of the performance degradation. So this can be more interesting for us. So that means it's already the certain important characteristic that has been shifted to a certain amount, and then we can consider that is a value as well. Actually, we in the semiconductor domain, we prefer to define as a certain degree of the performance degradation rather consider the actual breakage or actual fracture here. So for example, the performance degradation for sure is a certain degree of the shift and then can be usually defined by the engineers. For example, we probably can define the degradation that means our threshold voltage shift has been larger than 0.1 volt. So that means as long as our threshold voltage is more than 0.1 volt, that means this is already we can define as a value, or we can define our on resistance reach to 20% increase. This is our threshold voltage reach 0.1 volt shift, and that we can consider as a value. Or on the other hand, we can also consider once our R-on has been already 20% shift, that we can also consider as a value. And in reality, we actually more prefer to define this kind of the performance degradation as a value rather than consider the actual fracture or actual breakage for the one semiconductor device here. And then on resistance here, so we have been already shown previously. This is our typical IDVG curve. So initially we have the curve like this one. This is our IDVG curve, and then after certain operation we can clearly see the threshold voltage will shift to the right hand side, and then this amount is how we call as a delta VTH. So in this case we can define as long as our delta VTH is equal to 0.1 volt, and now we can consider our device already failure. Or on the other hand, another factor very often used is IDVD. So the IDVD for the one transistor is generally look like in this way. So usually we'll define this part as our on resistance. So this slope is R here. So that's usually we call as on resistance. So if once we have on-resistant degradation for more than 20%, and that's we can also define as our device has reached the values. So that means if we do the certain testing, and in the end we figure out our this kind of the shift has, this is delta R. So once we reach to delta R for 20%, then we can also consider this is a value here. So does it mean that a spec is not being met here? And if so, what's actually the spec here? So every time when we consider reliability, we have to be very clearly about the how do we define the values here. So despite these uncertainties, generally accept that the product value occurs when the required function is not being performed. And then the key quantitative measure of reliability is the failure rate. So this failure rate is at which a device or component can be expected to fail under the non-use condition. So basically we can try to calculate the failure rate here with a specific testing condition. Once we have failure rate, then that can give us a certain lifetime estimation. For example, if the failure rate if now we have a failure rate of 1% on increase, per week, and that means, but now our spec is a 20% defined as a value. So that means our device right now can have the 20 weeks lifetime to reach or delta R on equal to 20%. So this is a very simple calculation, but this kind of concept is very important because in the future, when we talk about reliability, for sure, first we will define the specific condition, and second we will define what actually the values we consider. And after we have the value definition, and next stage we need to try to calculate the failure rate. So once we have a failure rate, then we can start to do the estimation of a lifetime. So the goal for us is always trying to understand how long our device can be used. So these are the main target when we talk about reliability. One thing is how long our device can be used, and another thing is why our device will be failed below the targeted lifetime. So now the next is still, we need to make clearly for the another thing is about the failure modes versus the failure mechanisms here. The first one is a failure mode. So a failure mode is the failure mode is kind of the electrical symptom. It's an electrical symptom by which failure is observed. So that's what we call the failure mode. And what does it mean, the electrical symptom? So we can use the TDDB as one example. So if we have the gate current versus the time, so roughly we can have the TDDB degradation like this one with a certain bias. We start to see lead current decrease, and after a certain moment we start to see the current increase. So that means we start to have the breakdown, and this is electrical symptom here. So that's how we call as a failure mode. So this is the electrical symptom for the TDDB reliability issues. And for sure, there's a lot of the electrical symptoms can be happen. For example, you might have the short or open circuit. So electrical open device input and increase the current all modes of electrical failure. So in anyhow, short or open can be another failure mode here. And each mode, in principle, can be caused by one or more different failure mechanisms. So it can be have the several mechanisms in them that always lead to the one electrical symptom, one failure mode. So we can possibly to have the multiple failure mechanisms that in there always lead to the same failure modes here. So we can also consider, we can use a simple MOSFET as one example. So we have the source and drain here, and we have the dielectric. So we have a source, drain, a gate here, and then this is a typical front end schematic which only consider the gate source drain, but in reality we also need to have the interconnection line. So we also have to consider the lots of the interconnection line to connect the signal. And to isolate the signal between the interconnection line, we will have the passivation here. We have a loss of the dielectric. Try to isolate the electrical signal between each interconnection line. So if we consider the TDDB here, actually there can be two possibly mechanisms, but always showing the same, this kind of electrical symptom. So one is for sure, we might start to have the dielectric breakdown. So once we have the dielectric breakdown, then we can start to have the high gate current that can cause the TDDB issue. So the first one is TDDB in the gate dielectric. But on the other hand, if we consider the passivation is also another insulator. So that can be also possibly to have the breakdown between these two regions as well. So it's not actually liquid pulse, it's not happening of gate dielectric, it's mainly happen in our passivation dielectric here. So we can also have this TDDB phenomenon in the passivation layer. So now you can see with one electrical symptom, in the end, actually we can possibly to have two different mechanisms. So we can have two different mechanisms, but in the end, that always leads to the same failure mode. It always leads to the same electrical degradation. Okay, so basically, failure mechanisms are the specific microscopic, physical, chemical, mathematical, or environmental phenomena or process that can cause device degradation or malfunctions here. So that's a mechanism. So failure mechanism is a specific physical, chemical, or mathematical, or environmental reason that can cause device degradation or malfunction. For example, the open circuit. So open circuit is a failure mode. So this is a failure mode. This is a failure mode of the interconnection could occur because of several possible reasons. One is this one. The corrosion. And second one is because of too much current flow. So we can possibly to have these two failure mechanisms that always can lead to the same failure mode. So for example, in the case of open circuit, it can be due to first one, the corrosion, and second one is too much current flow. So these are the mechanisms. So another example is, for example, high electric field, dielectric breakdown in insulator. It can be another example of the failure mechanism. So therefore, we have to be clearly understand what's the difference between the failure mechanism and then failure modes. Now, as being a semiconductor engineer, one thing for sure we need to understand how do we do the characterization, how do we do the reliability testing. But after we start to found there's a failure mode happen in the semiconductor device, for sure the most important is to try to understand the failure physics, failure mechanism, because once we understand the physics and mechanism, that can give us a good way to how to further improve our semiconductor device here. And therefore, in here I need to introduce a concept. That's how we call the reliable and the fail states here. So the failure consists of a transition from the reliable to the fail state. So that's why the reliability is a time-dependent phenomenon. So this is a time-dependent process, because in the beginning it's always in a very reliable state, but after we operation for a while, we start to find out there's a fail state here. So failure virtually always begin through a time-dependent movement of atoms, ions, or electronic charge from benign state, benign side, that means a good size, in the device or component to the harmful size. From the benign size to the harmful side. So that means these failures is always a process of the time dependent from the reliable state to the failed state. But in detail, it's a time dependent of the certain movement. For example, it can be the atoms movement, ions movement, or electronic charge movement from the benign side to the harmful side, because it's in the end, these electronic charge, once they move to the harmful side, they can start to influence our electrical characteristic. And this electronic charge is mainly cause the issue, what we usually consider as a trapping. So in here, we need to start to consider what kind of the possible electronic charges can be happens here. If lost atoms or electrons accumulate in a sufficient number and harmful sign, and damage can happen here. So one of the example here is we can also use a simple MOSFET to understand how possible electronic charge can move. For example, we have the typical source, drain, and on top of this dielectric, we have the gate here. So we have a source, drain, and the gate here. And if you're trying to start to look at the band diagram from the gate side here. So in this class, we will not talk too much detail about the band diagram. This is the knowledge you should learn from semiconductor physics. But the band diagram is a very good tool, allow us to do the analysis, no matter for the static or even for the reliability analysis. So if you try to start to look at the band diagram under the gate region, so typically we can start to make the band diagram like in this way. We have the semiconductor, so that's our substrate, and on top of substrate we have the dielectric. So for example, in this case, it's a silicon dioxide for our case here. And then in the band diagram, we usually define the top line is a conduction band H, and the bottom is a valence band. And then the value between the EC and EV is a band gap. This is band gap. And now we have to consider that how actually the charges can be possibly moved here. So usually we have the metal here. This is our metal, and it's a place where we can start to apply the gate. So usually we will start to apply the positive VG here. So once we apply the positive VG, we start to pull the banding here. Of course, that we have already mentioned, once we apply the positive bias in the gate side, it is possible to start to have the electron inverted in the channel. So we start to expect electron inverted in this region. And electron inverting in this region, that also suggests we start to have electron generation in this region as well. So that's our electron. But the problem is, once we apply the gate bias, so since we have the gate bias here, we have the electron, which are the negative charges here. So we can start to expect this electron can have a certain chance being injected from the right to the left, because we have the positive gate bias on top. We have a negative charge below the silicon dioxide. So it's pretty straightforward that this electronic charge will tend to move towards the positive bias here. So that's how this text says that the value always begins through a time-dependent movement of the electronic charge from the benign side in the harmful side. So in this case, if the electrons is only stay in the channel, so that we can consider this is benign place. But the problem is that our dielectric is not always perfect. So we have so many defects inside this dielectric. So these are the defects. These are the defects. So as long as we start have the defect in the dielectric, but on the other hand, the electronic charge will also tend to move to the left. So that means this electronic charge can start to move from here to this defect place. Therefore, we can start to see this defect place are start to be filled with electrons here. So that's create the problem. That's how we call as a trapping. Because right now, the defects can capture the electron. And this phenomenon defect can capture the electron. This phenomenon is how we call as a trapping. So this is one of the example to illustrate that how the failures can be happen step by step. So as I say, the failure is a time-dependent process that electronic charge from movement from the benign state. And unfortunately, this electron will try to move to this harmful place. For example, to the region full of the defects here. And this defect can start to capture electron. And once defect capture electron here, that's cause the trapping issues here. We will start to find out that there's a performance degradations can be happens here. So that's one of the example that we need to step by step to further understand the value physics here. And this phenomenon is generally related to the later one we will talk about is a bias, temperature instability, and interface trapping. So this already related to one of the key topics that we will discuss in the later class. So since we have been started to talk about the movement of for example, atoms, ions, or electronic charge, and the next stage we start to need to understand what actually the condition that can lead to the change here. The first one is we need to back to the very fundamental. That's how we call the thermodynamic. So thermodynamic is a reaction naturally proceed when energy is reduced here. So in the transition from reliable to fail behavior, the energy of reliable state exceeds the energy of a reliable state exceeds those of a failed state, and the process must proceed at a certain rate here. And similarly, in the chemical system, two conditions are necessary in order for a reaction to readily proceed at a constant temperature pressure. So in here, we will start to talk about what will be the condition leading for the change, and we will use some of the basic knowledge related to the thermodynamic here. So when we talk about thermodynamic, so thermodynamic requires the energy of system being minimized. So therefore, we have to introduce a specific term. That's what we call the Gibbs free energy. So Gibbs free energy is an energy to measure the chemical energy associated with the atoms or molecules here. So that's how we call this as a Gibbs free energy. And the definition for Gibbs free energy is shown here. We have a delta G is equal to GF minus GI. So usually the delta G is a negative value, where delta G is smaller than 0. So the GF is a free energy in the final, or for example, the failed state here. And then GI is energy in the initial or reliable state here. But the problem is the Gibbs free energy would prefer to attain the most negative value as possible. So that means we prefer in the nature of the system, the delta G should be as negative as possible. Then this is what we consider in the state of the thermodynamic equilibrium. So once our delta G can achieve as negative as possible, then the system will start to approach to the case of the thermodynamic equilibrium. So this is important because later on we can use this concept of Gibbs free energy to understand why no matter what kind of the material, no matter it's related to semiconductor or it's related to human being, to all kinds of stuff in the world, the system, in order to reach to the thermodynamic equilibrium, all of the case that always show that the things will gradually change from reliable state to the failure state. And this is because due to this Gibbs free energy. So, and also, we can consider the Gibbs free energy can be corresponding to this. There are two primary ways that system can spontaneously lower its grid potential. First is by a decrease of delta H. Which is this one. Or by increase of a delta S. That's entropy. So that means if we want this to be negative as possible, either we decrease of this or we increase of this one here. And then you can start to see how the system that gradually move in order to reach the thermodynamic equilibrium. So these are the two examples that can have a spontaneous change. Although it looks like could be contradict to each other, but they both reach the same goal, is trying to have a lower Gibbs potential. So for example, in the beginning, you have this kind of you put a certain oil inside this container, inside this solution. After a while, the oil will try to accumulate with each other, and because this is trying to reach the concept of a decrease of a delta H. On the other hand, if you try to split some alcohol inside the water here, after a while, the alcohol will start to split here. This is because increase of the delta S. So these two examples might be contradict with each other, but in the end, the goal is the same, try to reach the negative delta G as possible. Try to have the lowest Gibbs potential here. The same concept can be applied to our semiconductor. So this is one of the example. We have the two metal on each side, and we have a dielectric in between here. So if we have a dielectric in between, and then because we have the positive bias in the anode and negative bias in the cathode, actually we can start to have the voltage difference that can lead into the polarization and fields here. But in this case, actually the Gibbs potential increase, but that's not the system prefer to have, because the system to prefer to have a lower Gibbs energy to reach the thermodynamic. But on the other hand, if we have certain short in between these two anode, these two metal, that's where is the anode and cathode, this can reach to the Gibbs energy decrease. So this is the case that system prefer to have, because that in the end can reach to the thermodynamic equilibrium. So Gibbs potential is defined in such a way that any spontaneous change in the Gibbs potential delta G can occur only if the change leads to a reduction. So that's a crucial, leads to a reduction. In Gibbs potential. So that means if we have a system that we have the dielectric here, the dielectric, because due to this dielectric that will separate the charge between top and bottom, and therefore there's an electric field here. But in this case, the Gibbs potential is increased. But to reach the dynamic equilibrium, actually, once we have a short happen in between, there's no more any electric field voltage drop here, that can reach the lower Gibbs potential. That can give us the system will prefer start to, in this case, because due to a thermodynamic equilibrium. So that's why if we don't consider all of the knowledge from semiconductor, we just purely consider this Gibbs potential. This also tells us that the whole system will start to prefer to move to from the reliable state to the failure state, because try to reach the minima of the Gibbs energy. Okay, so the work done as system material against conservative resist system force tend to increase the potential energy of system material. Therefore, work can increase the Gibbs potential. However, the increase of Gibbs potential makes the system material more unstable. Because the Gibbs potential prefers to decrease in a potential. So that means the increase makes the system more unstable here. But therefore, from a material in a stress state, then the spontaneous change and degradation in the stress material is expected. Since the degradation leads to the reduction in the Gibbs potential and free energy here. So that means once we have a stress here, and we can expect for a spontaneous change or degradation, because this degradation can lead to a reduction of a Gibbs potential of free energy. And the stress state here, that means we start to provide as additional bias or temperature in a one material. And the second requirement that can lead to the condition change is we need to have the kinetic. So once the reaction is thermodynamically possible, it must proceed at a certain rate. And the rate is proportional to the Maxwell-Boltzmann factor, also known as the Boltzmann or Arrhenius factor. Here, so equation 1.2 is an example how the rate is equal to A exponential minus delta G over RT, and where delta G is in here what we call the activation free energy. And T is a temperature and R is a gas constant. Because of this equation presents whenever degradation is thermally accelerated here. So in this case, we consider that the thermal or the temperature can accelerate the degradation. So the degradation is thermally accelerated here. So therefore, this equation is one of the most important equations that we will use for later on to understand how the temperature can accelerate the degradation. So this is what we call the Arrhenius factor here. So here is some of the additional example. If we consider the diffusions in the solid, so that's a chemical reaction here. So the Alton-Salmon energy barrier established along the reaction coordinate here. So from Alton to move from one side to another, the two conditions must be fulfilled. So that means if right now we assume we have the latest arrangement like this way, so we have the lots of Altons here. So if you have the one Altons would like to move from left to the right, the first condition that has to be reached is we need to have the vacancy at this moment, at this place. So that means because we need to have the vacancy, otherwise for sure our diffusion cannot be happen here. So the first two conditions must be fulfilled. The first one is we need to make sure there will be an available site. An available site for the Alton to move in. For example, the vacancy is an available site here. And also, the Altons must possess a sufficient energy. So the Alton needs to have sufficient energy to push Alton side in executing the required job here. So that means we have the, here is our so once we have these Altons want to move to the right, first we must make sure that there's a vacancy. And second one, because this Alton, once it moves, it requires a certain energy here. Try to move from the here to the here. So that means it must possess sufficient energy. In the end, to reach to the right place, like here. So this is the first one. It's a vacancy here. The second one, it must have enough energy, just like here, to push your atoms aside in executing the required jobs here. So the rate, diffusion, and chemical reaction are mathematically expressed by the same Boltzmann type of values. That's where we have been shown, where we show me here. That's how we call this kind of the diffusion equation, and where D is a diffusion. So, as already mentioned, the rate of diffusion and chemical reaction can be mathematically described by the Boltzmann type of value, as shown here. And to simplify, therefore, the delta G is replaced by the relevant activation energy. In this case, that will be the ED. And both D0 and ED are dependent on the nature of the diffusion matrix, the specific path taken by the atoms here. So the D0 and the ED is the factor that highly depends on the materials, highly depends on how this atom can be moved here. And the value D is a function of T for automotive diffusion in the metal semiconductor oxide as well. So that's the value of D. So that's a typical Boltzmann type of equation to describe the diffusion phenomena. But in the end, that's leading to the final equation that we actually will be often used. Is how we call this as a Arrhenius equation. So in physical chemistry, the Arrhenius equation is a formula for the temperature dependency of a reaction rate. So that was proposed by, in the early time, like 1889. So we already know that there's an equation, that's how we call the Arrhenius equation, that's try to describe the temperature dependency of the reaction rate here. But reaction rate, this term is not the term we often use in the semiconductor. But we have the one term exactly has the same meaning of a reaction rate. But in our case, we actually call this as a failure rate. So, as the previous already mentioned, our semiconductor, when we do reliability, for sure, first we try to understand the phenomena, understand the physics. And then the most important is we need to do the lifetime estimation. But once we talk about lifetime estimation, we need to know how fast this value can be happen. So that's why we usually will try our best to calculate the value rate here. So therefore, the concept has been using in the physical chemistry to describe the temperature dependency of the reaction rate. This kind of concept can be borrowed for us because now we can use a similar things to calculate the temperature dependency of a failure rate here. And this start getting more and more important for us, because once we know about the temperature dependency of failure rate, and finally that can give us the possibility start to calculate the lifetime in the different temperature condition. So let's back to the previous example. As we already mentioned, if we do the room temperature testing at VG at 5 volts, now we probably need to take more than 5 years to see the device will completely fail. Of course, 5 years is not a good timing that we can excuse in the lab or in the company. So therefore, I already mentioned, what we often do is we do the temperature accelerating testing. So we will heat up our device at 150 Celsius degree. And the purpose is, in this case, we still do the same for VG 5 volt. Now we can see our device will be failure with 1,000 seconds. And 1,000 seconds is a good timing that we can excuse. We can run the thousands device that all can be tested with 1,000 seconds, even in the university lab or in the certain of the foundry. But the last state is become the problem is, how do we convert the 1,000 seconds is a result from 150 Celsius degree back to the time that we prefer at room temperature. So finally, this temperature dependence of the Arrhenius equation give us this kind of possibility. Because right now, if we can know the temperature dependence of the failure rate, then we can start to apply this back to this one. And finally, we can complete our last step with convert the result of 150 Celsius degree back to the case at the room temperature. And this is usually require a specific number. That's how we call the EA here, activation energy. And we will talk about where is the activation energy in this slide for the following equation. So Arrhenius equation used to model the temperature variation of the diffusion coefficient, population of crystal vacancy rate, and many other thermally induced process reaction. So now I hope everyone can get more like the consistent understand now, because in the beginning we already mentioned that the temperature is a one universal way to accelerate degradation. But I think that's a pretty straightforward to everyone's daily experience, that once you put certain things in the high temperature, it always degradation faster. For example, if you put the food in the high temperature place, and then your food will start to be corrupt faster because of the high temperature will accelerate the degradation. In the case of food, that because due to the some of the virus or bacteria that can grow faster at a high temperature, and that's the same thing in the semiconductor. So basically, the temperature is a way to enhance the reaction, or in here we call, in chemistry we call reaction. But in reliability, we prefer call the degradation of value. So basically, the temperature is a way to accelerate the value and degradation. And now we come up with, we can borrow the experience come from Arena's equation. Finally, we can have the chance to model the temperature dependent, this kind of the process reaction here. And if you start to look at this equation, that's a K is equal to A exponential minus AEA over RT here. And in this case, the EA is the activation energy of a reaction here. But the R here is a gas constant. Of course, in our semiconductor world, we are not that interested in the case of a gas. But we can borrow this equation and reform in another way, where our K is equal to A exponential minus EA over KT here. And this is a case we are interested in because right now the K is related to the Boltzmann constant. So I think the Boltzmann is some of the terms you have been here again if you are in the semiconductor world. So basically we use the Boltzmann constant a lot. So once we have this equation, finally we can start to we can start to have this EA. So EA can be used to describe the thermally induced reliability, the thermally induced value. And we consider this EA, so we can start to do the things we are interested in. So finally, we can convert the values happen in the high temperature back to the any temperature we are interested in. In this case, it's a room temperature. So once we have this kind of the mindset, that can highly enhance our efficiency to do the reliability testing and also lifetime modeling, because we won't take 5 years. We actually need to only take 1,000 seconds, but with a proper activation energy. So finally, we can start to estimate. So now, if you have been in the reliability field for a certain time, if you start to look at the literature, you will find out that one of the key factors that every literature is talking about is definitely related to activation energy. So activation energy is the key when we talk about reliability testing. And if you look at the data sheet, if you try to buy the one product, one component, you definitely need to check the data sheet of this component. So the data sheet is basically a document to list all of the important characteristics here. And usually in the data sheet, they will also clearly specify the activation energy, because the activation energy can allow the customer to convert the time, to convert the thermally induced reliability to the any time that they actually would prefer to use. Okay, probably we will take the 10 minutes break and we will come back later for some basic calculation for the Arena's equation and Arena's plot.哦，好，我们再看好，对，等看你谈一下，因为这边它会那个录影一下，对。 Okay. Okay, so I think from this week we have the course selection is finished. So now we will do the first roll calling. So if you hear a name, please let me know. 陈玉安、王正照、卓宇腾、陈瑞宇、徐义熙、黄国文、洪成伟、廖玉杰、李奇阳、柯宏泰、吴奇洛、廖伯全、李金豪、杨志豪、朱义文、刘继煌、彭修颖、陈其安、沈博君、黄之涵、汪潘爱玲、Yvonne、Anna、张怡良、史淑慧、谢立伟、孙乃全吗？郭安成、杜瑞慈、陈怡轩、崔定和、魏玉婷、魏宇阳、陈新威、胡家敏、张浩伟、黄成颖、李进佳、陈鹏萌、林佑廷、郭品轩、高宇和、李炳轩、卢沙特、谭义雅、潘氏经营、陈鹏宇、王松纯、常佩杰、萧元玉、蔡庆辉、邱冠祥、陈定乾、刘桂红、林冠汉、邓有福、周燕婷、戴文祥。Okay, so now we'll continue. So, we have been already discussed for the arena equation, and the next one is we have to teach you how to calculate the activation energy. And this actually is not that difficult, although the understanding might take some time, but if you try to analyze the activation energy, then the calculation sometimes is rather simple. And typically we will try to build up the arenas plot here. So the first one is we have the arenas equation as previously have been shown. The K is equal to A exponential minus EA over KT here. So this just involves pretty like basic high school mathematics. So we put the natural log K here, and that will be equal to natural log A minus EA over K times 1 over T here. So then we can start to reform this equation as shown me here with minus EA over K 1 over T plus natural log A here. Then as long as we try to build up the equation is equal to Y is equal to mx plus b here. So that would be Y is equal to natural log K and X is equal to 1 over T. And therefore we can simply make the graph like here. We have the natural log K in the y-axis. If we choose a y over t as the x-axis, then we can make the graph. If we try to have the different temperature characteristics, so then we have this one, and in the end we can simply make the straight line as shown me here, and then the slope is equal to minus EA over K. So then in this case we can start to estimate the activation energy. We can start to estimate the activation energy, and then the K can be the any quantity that we are interested in. For example, the threshold voltage shift, the arm increase, or gauge current increase, and so on and so on. As long as we pick up one reliability characteristic, for example, probably the threshold voltage, arm, and so on, and then we can just make this quantity versus 1 over t. Then we can build up this arenas plot, and then we can have the activation energy. So that's the pretty like easy way that helps us to calculate the temperature dependency of the certain value mechanism. So, if a driving force or bias did not exist, then the atom will migrate with equal probability. In the opposite direction. So that means if we assume there's atoms here, but we don't give the bias, and therefore this atom will migrate left and to the left and to the right with equal probability. So in this case, we can consider there's no net displacement for this photon. But on the other hand, when we have a driving force or field start to apply on the photons here, then we can start to see there's a certain band bending can be considered in this energy barrier here. So this graph we have been shown previously that we have the one photons try to move to the left, in the middle, and to the right here. But this process can be also described by consider this energy barrier here. So this is a case where we don't apply any field. So our photons is sitting in this place. But right now, if we start to apply the electric field, so once we apply the electric field, definitely this will change something in this energy barrier. So now our free energy barrier will become like in this way. This is under the case where so this is under the case where we have applied force in this direction, F here. So now if we consider the place 1 and place 2, the place 1 has a delta G star here. And then the place 2 has delta G star plus delta G here. So photons in place 2 have a lower energy by amount of the delta G compared in the place 1. Show me here. So this place has a lower energy delta G compared to this one due to this additional delta G here. Therefore, by consider this schematic, then we can start to calculate the rate. So the rate R12, this is rate between 1 to 2, can be expressed as a V exponential RT minus delta G star minus delta G. And also the rate between 2 to 1, R21 is equal to V exponential RT minus delta G star plus delta G. So that's the rate between 2 to 1 here. And therefore the net rate, which will be equal to R12 minus R21, which is equal to this equation. And this can be that's how we, where the V here is equal to this one. That's how we call the Nernst-Einstein equation. And this important formula is valid in describing both chemical and physical change induce the diffusion motion of the atoms here, and where the V is equal to this one. So that's the equation allows us to calculate the net rate under the considering of the diffusion process. And in addition to the diffusion rate, the net rate we have been discussed before, now actually this is getting more important to estimate the failure time and also the acceleration factors here. So we have several terms here. So the first one is what we call the mean time to failure, MTTF. So the mean time to failure by definition is MTTF is equal to, if we test for the multiple device T1, T2 plus Tn over n in total. So that's the MTTF, mean time to failure. The reason why we have to calculate the mean time to failure is because if used as a TDDB as example, we already mentioned that the reliability is a random process, and then sometimes we call it stochastic. That means we can only estimate by considering the statistic, not be able to estimate precisely. So that means if you test one device, it's indeed you will see this kind of curve. So then you can define this one as a T1, the first device where has a T1 that reached to the time to break down. But the problem is, if you test multiple device always shows a different time. It is impossible that all the devices will show in the same T. So therefore, you can possibly have the curve for another device like in this way. And you can have the curve for another device like in this way. So we have T1, T2, T3. So that's why we have to define. That's how we call the mean time to failure. So in this case, the MTTF is equal to total. We have 3 devices. Each one is T1 plus T2 plus T3. So that's the MTTF here. On the other hand, there's a term, that's what we call the mean time between failures. That's what we call the NTBF. NTBF is equal to the difference between each failure. So that means this is equal to T2 minus T1 plus T3 minus T2, Tn minus Tn minus 1 over n here. So that's a mean time between failures. And also there's another term, what we call the median time to failures. Median time to failures, that's what we call the, for example, T15. So that means a curve when 50% of a device that have value. That's how we call the T50. So that means you test, for example, you test for 100 devices, and then you found out that there's a time that the 50 device reach to the value. So this is the time we call the T50 percentage. Of course, in reality, T50 percentage is 50% of the time that reach value is actually the pretty high amount of the value percentage. So usually T50 percentage is not our final interesting factor. We are more interested in the case, for example, T1%. So this is a time that reach to we have 1% our product fail. So this probably is a 1. We are more interested and more practical for us. For example, once you make like the thousand of your device, probably you will be interested in only 1% data, 1% value data, rather than the 50% value data. But we still need to talk about T50 percentage, because later on, also, there's another very often used number is called the T63 percentage. So T63 percentage, that means we have the 63% value with a certain time. And later we will discuss why it's come up with such weird number of the T63%. It is mainly due to some mathematical calculation. But T63% is important because we will use this number when we talk about the Weibull distribution. So basically, if you are in the semiconductor domain, you cannot possibly to avoid the concept of a Weibull distribution, because Weibull distribution, just like the Boltzmann equation, like a Boltzmann or Max Planck, these all kind of the famous term that actually is come out in the end is everywhere. In the everywhere domain, we always use this kind of very classical and epic mathematics allow us to understand the semiconductor device behavior, or if we try to use this equation for the semiconductor modeling. So we will discuss the Weibull distribution later. And the NTTF is used to describe or model the physical value time. On the other hand, T50 will mostly arise in the statistical or mathematical analysis of value distribution. So we will talk about T50 or T63 later when we talk about the distributions. Also, by considering the NTTF, finally we can start to calculate the acceleration factor. So the calculation here is rather simple. The most important is the concept. It's not just like, it's not a calculation. So all the calculation now actually can be done by the lots of the software. Lots of many software can be already perform this kind of a calculation. But the most important is to understand the concept, to know when we are be able to use this formula. So the acceleration factor is defined as NTTF T1 over NTTF T2. So that will be equal to exponential delta G star over R, 1 over T1 minus 1 over T2. So the acceleration factor is defined as a ratio of the degradation rate at the two different temperatures. One is T2 and one is T1. So as you know, temperature is become one of the way we are trying to accelerate the degradation. So we will definitely be interested in how to quantify the acceleration coming from the temperature. So that's why we come up with this AF to calculate the degradation rate ratio between the one temperature referred to the another temperature here. So the simple calculation can be just described here. If we consider the T2 is 150 Celsius degree, and then if the T2 we try to test the device reliability in the 150 degrees, and our NTTF is equal to 100 seconds. And then we try to test at the T1, where our T1 is the room temperature and our NTTF is equal to 1000 seconds. So our acceleration factor just can be calculated like 1000 over 100 is equal to 10. So in general, the calculation here is very simple. It's not that big deal, but the most important is to understand these different terms, the meaning between these different terms, because we will use this term again. Okay, so generally, as the temperature increase, the atoms vibrate at a high frequency and move further apart. First, the high frequency of the vibration energy kT means the atom pump into the space between the atom more frequent with a higher energy. So what does this mean? It means that if now you have a lattice arrangement like here, this is a room temperature. So now if you have a one atoms in here, but once you go to the high temperature, this is another explanation why the high temperature always drive the degradation faster, because of the two reasons. One is at the high temperature, and again we still have the atoms here. So first one, as a high temperature, of course, there will be the higher vibration energy. So that means that the atom will vibrate more frequently than at the room temperature. So we can start to foresee this atom will try to vibrate more at a high temperature. So this is the case at a high temperature. And on the other hand, at a high temperature, the distance between each atom is become larger. So that means this atom is getting more easily jump to another place and jump to another place. So we have a large distance between the atoms. So that's why we can foresee at a high temperature, your atom will get more easily to move to the other place because of two reasons. First one, due to the vibration energy, so this atom will try to vibrate in the higher frequency than compared to the case of low temperature. The second one is the space between the atom is getting larger, so that means this atom is getting more easily jump to here and jump to here. So this is actually how this text is talking about. First, the higher frequency of vibration energy means that atom bumps into the space between the atom more frequently with a higher energy. And second, the space between the atoms are larger on average because the center to center space increases the temperature rise. So, because due to of these two reasons, the temperature accelerates rate, that which considers a bad effect will start to happen. So we will start to foresee the temperature acceleration. In a sense, temperature has a twofold effect as described above. The first, there's more energy driving the reaction or diffusion rate. And secondly, the reaction diffusion will take place more easily because due to the large atom to atom space here. So that's why the high temperature can cause easily faster values, the faster degradations. And another is we can also use this low strength interference to describe why the values can be happen after the certain of time. So in the beginning, we have the strength here. We have a load here, strength and load here. And then with the time, the strength means that how good of your material or certain how strong or your material is. But with a certain time, our strength will start to getting weaker and weaker. So we can start to expect so the load is the same. The load means that the how much amount of you can imagine this is a kind of like the something you want to carry, so that can be considered as a load. So something you need to carry is the same, but your strength, your power is degraded. So that means with a certain time, the strength here is start to degrade. But in reality, we are not only consider the one case, we have to consider the distribution, we have to consider amount of the component always exhibits a similar phenomenon. So therefore, we put the distribution factor here. So this is distribution for our load. So this is distribution for load. And this is distribution for the strength. Strength is kind of like the power. Like for example, if you want to carry on something, the strength can be the something can be the load, and the strength can be, for example, like your muscle and so on, your body, how much the load you can lift off. So that can be considered as a strength as well. And problem is with respect to time, the load won't change, but the strength is decreased. And once it's decreasing more and more, we start to see the overlap between these is getting, overlap region is getting higher here. So once the overlap region is higher, that means the failures can start to happen. So this is another illustration to help you to understand why in the end the failures can happen. It's because of the strength is decreased, and then we have if we consider the distribution, that means we have the amount of the strength that can have a highly overlap with the load, and in this case that we can start to see the failure is coming. And one last thing is also important is we need to understand these best tube curve and related to the failures here. This best tube curve is really famous. It's not only describe the case in a semiconductor, it can be only described in the case like a human being as well. So again, we plot in this case, and then the x-axis is the time, and then the y-axis is the failure rate. So now I think you start to get more aesthetic with the concept that once we talk about reliability, it's always related to the time. And once we talk about reliability, we are always interested in like the failure rate, acceleration rate, because it's all related to how do we model the failure. In the end, how do we estimate the lifetime here? So in general, no matter what kind of the product or even for the human, it's the same. We always have the three phases of the failure time with respect to the time. The first one, we have a three phase here. The first is we have very high failure rate in the beginning. This is usually we call the infant mortality. And this is because you can imagine that usually if you consider a real life, no matter for human or for the animal, it's always the same. When they first to be born on the earth, in the beginning, they have the higher chance to get some problem, no matter for the sick or accidentally to lose their life, because in the beginning, they are very weak. They can be suffer for lots of disease, or they probably has some initial body issues. So that's why we call this infant mortality. So in the beginning, it always has a higher failure rate. And after a certain moment, once a life or product has been passed by this infant mortality, the next phase will be the useful life. Just like us at this moment. So in terms of our whole life right now, we are being quite useful now because of we have pretty low failure rate. We get a less chance to get a disease. Even we have sometimes suffer some things, but that actually won't hurt us a lot. So this is true no matter for the life or for semiconductor device. So usually this is a phase we call the useful life. But the last one can be beyond certain age. I think right now normally our human the life for our human is getting longer and longer. So probably like after 80s, after 90s, we start to face another possibility to increase the failure rate. So this is a region where we call the wear out. So you can consider this is a 3 phase for the human life, but that's also the 3 phase for the one semiconductor product as well. So the first one, the infant mortality, is also called the early failure. During early life, the failure rate is high since the product probably contain lots of growth or manufacturing defects, and that did not survive. So this is a region because in the early time that the product probably has a lot of defect or lots of malfunction issues. So then the early rate is higher. And then we always hope our product can be used in this region because it's a pretty longer time that our product is pretty stable with a low failure rate. And to make sure that we can screening out these, screening out the device product that possibly to have the infant mortality or early failure, we need to introduce a screening process. So product that must be survived with a certain, like the testing. For example, that's how we call the burn-in. So we will try to give us our device stressing at a high temperature and with a different voltage and to different cycling before the shipment here. And then this is a process we call this is a process before the shipment. So this is what we call the burn-in test. For example, this is the idea that if you now fabricate, for example, you have a 1,000 device that you already fabricate, but you don't know which one has this early failure. You don't know which one can be survived for the useful life. So you cannot sell all of them immediately because probably your customer will get some device that probably has a higher failure rate, just like in this case with the infant mortality. So usually in the industry, what we usually will perform is we call the burn-in test. This is kind of like a screening process. So screening is if you talk about the English word, the screening, for sure screen has a lot of different meaning. But I think in the screening here is mainly related to the filtering. Try to remove some bad device. Try to remove some device that can exhibit the early failure. So in the Mandarin, the screening process here is we usually consider like the section. So the purpose is to filter out the weak device that have the early failure. So once we do the burn-in or screening test, we probably found out that there's a 900 device can survive until the useful lifetime. So we will only sell to our customer with this 900 device. We will not sell all of them. So they will be the they will be the 100 device that can have the early failure. So in this case, $100 device will have the early failure. But 900 device is actually being proved that can be used in the useful life. And therefore, then the question come to the mind is that how do we do the proper burn-in test? How do we do the proper screening process? It's actually the big, the deal. It's a huge challenge because the screening, you need to make sure that you can filter out the early failure device and make sure that your screening process can really prove that this selected device is really robust in the useful lifetime. So if you look at for the literature, you try to look at the literature, you will find out that there's thousands of papers talking about how to conduct in the good burn-in test to filter out this device to prove that device is good enough for useful lifetime. And even you try to look at the burn-in literature, you will find out that there's thousands machine. It's a machine who dedicate for this burn-in test. So it's not just like the single device testing in the lab. It's actually a commercial tool that company will purchase to do the industry level burn-in in the end to make sure that the device can be qualified, being used for the lifetime here. And by the way, why is this called the bath tube curve? Because this curve, it looks like our bath tube. So what's bath tube? 浴缸. So that's why this is called the bath tube curve. So if you are trying to look at the Google, you look at the bath tube, you will find out that thousands of articles talk about semiconductor reliability. They all refer to this curve to explain that why the reliability is important for semiconductor device. Okay, so the next is, of course, when we talk about the failures, always keep in mind that we need to understand when, how, and why. So that's always the question we have to continuously ask us. So if you look at these triangles here, so there's three important questions here. Is, for example, when will this failure happen? And the next is how. And the last one is why. How this failure happen is because we do the stress. It's because of due to the additional issue. And in the end, we need to understand the reason, the mechanism. So that's related to the why. So for the when, for sure, we have the three phases that's already talked about. It can be happen in the infant phase or middle line, or in the end is in the wear out region. And when we talk about how, then we have to identify the failures come from, for example, gradual degradation or sudden degradation, or even like a catastrophic degradation. And for the why, so we need to understand it's randomly happen or is preordained. So these are the question that we have to keep ask by ourselves. And the difference between the catastrophe or the gradual also can be considered as a TDB as a one example. In some of the case, you will see the curve is look like in this way. In some of the case, you will see like in this way. So in this case, this is sudden increase, and this is gradual increase. So these are all actually imply something. This carefully observation of this curve that can highly help us to understand, because these two curves, no matter for sudden or gradual, that's already tell lots of story that help us to understand why the device will fail. And when we talk about the approach to the reliability physics, there's several approaches nowadays people very often use. The first one is empirical approach. So that's mainly based on the experience here. So we have a all set the computer observe frequency of the field return, and then we create the historical database to predict what's likely to happen to your next product. So basically, this empirical approach is based on our experience. So we do thousand times of testing, we collect all the data, finally we come up with certain empirical observation, empirical experience that can help us to do the reliability analysis or reliability prediction. And second part is a statistical approach. So we consider each component has a certain failure rate, for example, exponential minus 80, and then with a certain connectivities. So use the rules of a probability to predict overall reliability of the system. So that's a statistic approach. And then the last one is the physical approach. So we study the physics of an individual device, and then to understand the origin of A as a function of voltage, temperature, and etc. here. So that's a physical approach. So in this class, we mainly focus on statistical and physical here. Because the empirical is basically just collect the data and make the data, it's just like a big data approach. So you just collect all data and try to find a way to feed all this data. So that doesn't give us a certain physical base meaning, but in here we are more considered using the statistical and the physical approach. So this is one of the examples that to understand the margin of the safety. So this term probably is the first time for you, but if you are still in the field, you definitely will hear this term again and again. So what we have already mentioned, failure time, the early failure, the burn-in, the exertion rate, the Arrhenius equation, activation energy. Now the margin of the safety here. So for example, just use this is a real life example. We now try to pull a piece of the string. Pull this piece of string toward the right here. So then we can start to analyze. The y-axis is a strength. So this is a certain strength that we apply on this piece of the string. And then this is a stress here. So once we pull towards this one, it's still safe. But beyond certain, we start to see the broken in this place. So therefore, the strength of this material versus stress probably will be like in this way. And then, so that means this is a green one. This is green, yellow, and last one is here. So that's a failure point. But what does it mean, the safety margin? The safety margin is here. This is our safety margin. So that means you can pull this string until this one, but without damage of our string, without damage of our material. So basically, this is a safety region that you can use for our string. So although for the first time view, who might hear the safety margin is pretty confused, but to be honest, if you look at this real life example, that's just a safety region that for your product, safety operation region for a product. But in this case, in the semiconductor or reliability, we actually quite prefer to use the word of the margin rather than the region, because region is it's a word that can be used in too many occasions, so sometimes being very vague. But margin is a pretty specific term that can really point out that when we talk about margin, it's mainly related to the reliability. Okay, so I try to finish this chapter today. So, and the last one we talk about is the series and parallel system. But also, this concept is pretty simple. That I bet you already learned this in the high school, but you just forget it, and you just don't know that we can also apply this in the semiconductor. So series, just if you consider that you have the two components side by side connected in the series way, so that's the series system. And in this case, how do we determine the value? For sure, it's simple. We just times the value for each one and each one. So we call the overall the system value here. So that's the series systems here. Another, of course, there's another called the parallel system. The parallel means that we have the two component connect in the parallel way. So we have a PA and PB here. And then the values can be calculated as shown here. So if you look at some very fundamental probability classes, you will probably already know this one. So we can always use this one in our semiconductor statistic analysis. So we will talk about later. So this is some more detail. This is a full equation for these the previous two cases. So in here I won't talk too much because that's be impossible to be understood if you try to look at some basic definitions. Okay, so this is last part. So overall reliability is probability. It's always related probability with a time under specific condition without value. So that's come up with a question that we should know the probability. We should consider the time factor. We should clearly define the specific condition. We should also clearly define the values here. And also we talk about the thermodynamic and kinetics. And then the most important is Arrhenius equation. Try to give us a way to calculate the activation energy. And then these Arrhenius equations, activation energy, give us a way to estimate the thermally induced reliability values. Of course, we already discussed NTTF, NTBF, mean time to values, low strength, and best tube curve. Okay, so I think this is what we have today. So we will stop here and see you guys next week.